Welcome to Mr. Coger's classroom. I'll be doing kinematics today, specifically one-dimensional kinematics. It's the study of motion. But before we get really into what kinematics is, I need to talk about our entire first quarter. Our whole first quarter is dedicated on mechanics. Okay, the mechanics is the study of how objects move, how they interact, how they work together, the things that create the motion, such as force, and energy. So kinematics, the first thing we're going to talk about is actually motion and describing the motion. We don't really care why it's happening, how it's happening, what reasons it's happening. We just want to know how it's happening and can we predict with it? Can we get a good idea of where it's going? The second unit we'll be covering, which is dynamics, is about forces. What actually makes the motion happen? Well, that's a force, and that's dynamics. After that, we'll talk about translational motion, which is our main focus, which is everything linear based. Now, some of you may be surprised that parabolic motion is kind of a linear motion, just in 2 dimensions. But there's a separate type of motion that's not translational, not left, right, up, and down, in or out, and that's circular motion. That's where we're going to end our topic of mechanics. It's a little bit different, a little unique, one of the traditionally trickiest topics in our course. I have a couple little pictures there to go with them, just to give you an idea. So let's get back onto kinematics. When we talk about motion, well, the first thing we got to talk about is, well, where are you? How are you moving? What are you moving? How far are you going? So we're going to make a couple real quick key terminology decisions today. And it's very important to know the minor differences. Distance and displacement, now hopefully you're familiar with both those words, may be interchangeable to you before today. They're synonyms. If you pull out a thesaurus and look them up, they're going to be right next to each other. They have the same definition. But in physics, we're going to have a minor difference between them that means all the difference in the world. Distance is simply how far you move. If I take 2 steps right and then 2 steps left, my distance is 4 steps. Okay? I've moved 4 steps. Okay? If you think about when you drive a car, this is the amount your speedometer has gone, or your odometer has gone up. If you've driven 3 or 4 miles, that's how far you have moved. How far have you gone? That is distance. Now, displacement is something entirely different. It's the change in position from one place to the other. The common phrase we use is as the crow flies. A straight line, right? Straight line, shortest distance between points. That's what we're measuring. So again, if I take that example of I taking 2 steps to the right and 2 steps to the left, my displacement is actually 0 because I haven't gone anywhere. Okay. We'll talk about this as we move on today, but that's the base idea. So let's see if you can understand this. So I've got 2 paths. I've got the red path, I've got the blue path. I'm going from point A to point B. Maybe it's your crazy cousin who takes the red path the long way to school, you take the short way to school. Maybe you have a helicopter instead of having to drive. Who knows, whatever reason it is, but we got 2 paths. Well, which one's the greater distance? Are they the same displacement? What's going on here? What are they in terms of distance and displacement? Well, the first thing I hope you recognize is the red path is longer, right? It's not a straight line. So that means I've gone a farther distance. But I've started at A and finished at B for both of them, so my displacement is exactly the same. Okay. They're the exact same displacement. Okay. So, can you come up with 2 examples on your own? 2 things that, for instance, have some distance, but 0 displacement. I love this one for PE teachers. I'm going to give you a joke to tell them all the time. You know, how many of you have to run laps, right? Just tell them I don't want to do it because it's 0 displacement, right? Because you run a lap, if you run a lap, you start and stop in the same spot, right? So you have a 0 displacement. We'll talk about why that's different minor details later about it. But running a lap, starting in the same spot as you end, you've done nothing in terms of displacement. Okay. The other example is if you're one of those like emo people that are, oh, it's so the world is such a terrible place and we don't do anything and we're worthless. Well, here's a 0 displacement argument. Don't we all wake up and go to bed in the same bed every night? Yep. That means we do nothing. We don't go anywhere. We have 0 displacement. Okay. But of course we're actually doing things. But 0 displacement, major difference between distance and displacement. So, now, we have 2 new terms to describe the difference between distance and displacement, and we'll continue this description throughout our course. And that's the idea of scalars versus vectors. Okay? So what does a scalar mean? Scalar is a magnitude. It's a number. Okay? Now, what a scalar doesn't have into it is a direction. If I take 2 steps, that's a scalar. I didn't say to the right. I didn't say forward. I didn't say back. I just said you take 2 steps. Now, if I say I take 2 steps to the right, now the rules have changed. Not only have I given you a magnitude, 2 steps, but I've also given you a direction. And when I give you both of those quantities, we call those vectors. A vector has a distance, it has a scalar part, it has a magnitude part, but then I add into it that direction. Where am I actually going? And distance and displacement are exactly like this. When you travel 3 miles, okay, that's a distance. Okay? I don't know where I went. I could be exactly where I started if I went 1.5 miles and then 1.5 miles right back. I've gone 3 miles. That's a scalar. That's a distance. If I went 3 miles west, 3 miles east, 3 miles north, that's a vector. That's a displacement. My position has changed by that exact amount. So let's do our first real quick example. I'll give you a minute here, give you a second. If you have to, pause the video for a moment even, and try this problem. So a person travels 90 miles east and then 40 miles west. Now, as you see here, I'm going to use a little bit of graph paper. We'll talk about setting scales and such. That's advantageous. And I want you to answer these 3 questions. First one is, well, are they vectors? Second one is, what's the total distance traveled? And the third one is, what is his displacement? Okay. Very simple example. All right, so hopefully you've gotten it correct. So I'm going to jump over here to Promethean Planet, and I'm going to write on the board here. I got to go back. Those are some examples we'll be doing later. So, are the values vectors or scalars? Well, they've got magnitude, but they also have direction. So both of these are vectors. Now, what's his distance traveled? Well, that's pretty simple. Well, he went 90 meters first, and then he went 40 meters after that, so he went a total distance of 130 meters. Now, the displacement is where it gets a little bit trickier. It may require a little bit of thought with your graph. So I'm going to even draw this to scale. So I'm going to say he starts here, solid point there, and east is to the right. Hopefully you know your cardinal directions by now. And I'm going to do a scale of 10 to 1, which means for every mark I'm going to go 10 meters. So I'm going to say I go 10, 20, 30, 40, 50, 60, 70, 80, 90. Now I want you to notice how I drew a vector. You always start with the tail, which is a solid point. You draw a line to wherever you're going, and where you finish, you're going to draw a head. And that's so you know how far you've gone, the length, the magnitude, but also where you went, how you got there, what direction you went in. That's what the arrow's telling you. Now, I'm done with that one. So now my starting point is here. And my second vector is west, and it's 40 meters. So again, 10 to 1, I'm going to go 1, 2, 3, 4. That's 40 meters. Again, I put a head on it, telling me what direction I'm going in. So, what is my displacement? Remember, displacement's a change in position. I was initially here, I'm finally there. There is my change in displacement. That's how far I've actually moved. How much is that? Well, I hope you recognize with a simple little bit of subtraction, it's 90 meters minus 40 meters, and it actually comes out to be a displacement of 50 meters. So, big difference in numbers, 130, 50. You know, smaller than even the initial one, bigger than both. So you just got to be very, very careful on how to do these. Now, going back to our PowerPoint presentation, let's make a real quick note or two here. The first one is this. Vectors are always drawn from the original position to where it's going. It's always drawn with a tail first to a head second. When you draw a second vector on top of it, you start at the new vector, the end of the new vector, and move on from there. Now, luckily, they're pretty simple at this point. We're going to be doing them over the next 4 or 5 blocks. And really, we're going to continue them through the rest of the year. So by the end, you'll have lots of practice with vectors. Okay? But I'd also like to go ahead and give us our first formal definition, our first formal formula. This is something you probably should take an index card out at some point and make a displacement on one side, write the equation on the next. This should be memorized. And that is, displacement is current position, wherever you currently are, minus your previous position or initial position. And I want you to notice a couple symbols we have. We'll define them in a moment. Delta you should have seen before. That's from Algebra 1, Algebra 2-ish area. It stands for change in, right? So it's my change in x, my change in position. Okay, x standing for position, and x stands for current. That little not value, that means initial. So whenever you see x sub 0, that means not. That's always your initial condition, no matter what we're talking about. So let's continue talking about position and direction a little bit more, and let's talk about our symbology. We just did a little bit, let's do a little bit more. The first thing is, what letters do we use for position? Well, the first one is, I can move left and right is generally, well, if you think about your Cartesian coordinate for a minute, that's x. I can move up or I can move down, and that's y. And then, of course, that third dimension one that tricks everyone, I can move up, in, or I can move out, and that's my z direction. Okay? Again, you can just think of your Cartesian coordinates. Hopefully that makes sense. So you have to understand that all of these are positions. I can use x, I can use y, or I can use z, and it's trying to give you a little bit of hint about what type of motion we're doing. Now, we also have some predetermined directions. X is positive to the right. X is negative to the left. Y up and down is positive and negative. Z in and out. The last two we use, I want to mention the first one. If you're taking this with calculus, you're never going to use x, y, or z. You're always going to use s. S is your generic term for displacement. It's used in calculus mostly. What it basically says is towards the object, or towards wherever you're going, is positive. Away from wherever you're going is negative. Okay? We're going to use S a couple times. When you do a ramp, right? A ramp, it's moving in one dimension, but it's kind of moving up and down and left and right. So we might use S just to describe the motion along the ramp. Less complicated than thinking about two dimensions. We can still think about it in one. Now, the last one is very, very, very important. When you see D, that is when we're talking about the scalar term. That's when we're talking about distance. It has no direction, and it's just a number. Okay, so please make sure you never throw D in there when you're not supposed to. Okay, D is only for distance. Again, really quickly, let's talk about those two symbols. Not, the little zero, stands for your initial condition. The delta stands for change in. Obviously, slope's a great example. And of course, our displacement formula that you've already been given. So, now that we have a decent feeling about displacement, we need to talk about what happens when your displacement happens over a time period. Okay? And hopefully we all know what that is. That's speed or velocity. Now, again, this is another one of those things you bust out the thesaurus in the English class and you say speed or velocity. Your English teacher's going to go, that's the same thing. And I'm going to tell you they're not the same thing. They're entirely different. Speed is a scalar. Velocity is a vector. Okay? So, vectors get vectors. Scalars get scalars. So distance is going to relate to speed, and displacement's going to relate to velocity. So, let's talk about them. Speed first. Average speed. We're not talking about having to worry about anything crazy over a certain amount of time. It's just the distance you travel over the amount of time it takes. Okay? You write that in this equation, d over delta t. Notice, I'm using d here for distance. That's our term for distance. Now, velocity, on the other hand, is a vector. Okay, so we're going to use displacement. So average velocity is displacement over time, or delta x over delta t. Now, what you're going to find out is this. When we only have one-dimensional motion, we're usually going to call it delta x, or we're going to call it x. That's our default. It doesn't mean that y or z or any of those other terms aren't okay. It's just that that's our default. So when you look at your formula sheets on the AP exam, it's always going to be x. Okay, that doesn't mean it had to be left and right. It could have been up and down. It could be s. It could be lots of other values. But it's relating to displacement. Okay? Now, what are your units for both speed and velocity? They're the same. It's a distance, which is in meters, over a time, which is in seconds, which should be from your summer assignment. If you've done that already, you know some of your base units. So meters per second. Now, that's our base unit. The other one we'll see is kilometers per hour. And again, in that summer assignment, you should have seen me show an example of how to convert from one to the other. So that shouldn't be too big of a deal. Now, the last real quick note, physicists tend to be lazy with notation from time to time. And the thing is, time is very rarely taken at a moment. It's always a change in time. And because of that, we get tired writing delta t over and over and over and over and over again. You're going to see t all the time. And t always stands for a change in time. So what you're going to find out is, more often than not, the delta in front of time is going to drop off. Just because we're thinking of it as elapsed time. How much time was there? So if you see the delta drop off of t, don't freak out. It's still a change in time. It's just something we happen to do because physicists can be lazy from time to time. So again, at this time I would say pause your video, take a look at this right now, and attempt these three problems. Take 5 minutes, maybe 3 minutes. These aren't too terribly difficult. When you unpause it, I'll show you the answers. All right, hopefully you've gotten the answers figured out. Again, I'm going to jump over here to Promethean planet so I can write on it. So we've got 3 examples. Okay. A family trip goes 400 kilometers away, and the trip took 4 hours. The car's odometer went up 500 kilometers getting there. What is the average velocity? What is the average speed? Now notice, I made you do that conversion from kilometers per hour to meters per second. We're already in kilometers and hours, so I'm going to leave it in that at first. We'll convert at the end. So let's talk about which one of these guys are my displacement and which one of these are my distance. Okay? On the map, I'm 400 kilometers away. That is a straight line effect. That is a displacement. So I'm going to say that is a delta x. Okay? I'm going to call that a delta x. My odometer, the way the car moved, left, right, up, down, it didn't go in a straight line, that is my distance traveled, d. Okay? So I have 2 equations. I've got average speed and average velocity. So let's say velocity average is delta x over delta t, which of course is 400 kilometers divided by, let's see, how long did it take me? It took me 4 hours. Well, that's 100 kilometers per hour. Oh my God, that's super fast. Not really. That's about how fast we drive. Remember, this is not miles per hour. Kilometers per hour are not miles per hour. Okay? Miles per hour are a little bit faster. Okay? So if I wanted to find average speed, okay, so I'm going to say speed, which is speed, distance over time. Again, I'm still writing delta t. I don't know. I'll get lazy of it eventually. Is a total of 500 kilometers in 4 hours. And I think that's about 125 kilometers per hour. Okay. Now, how do you convert from meters per second? I think I'm going to leave that to you. Okay? When I check this homework, I'm going to make sure you made that correction. Please do it. There's in the math help an example of how to do this if you're not sure how to. Part 2. If a person runs 7 meters per second, how far can he run in 200 seconds? Well, that shouldn't be too hard again. Velocity is delta x over delta t. I'm looking for how far he went, okay, or how far he displaced in this case. So delta x, with a simple mathematical thing, is rate times time, or velocity times time, which is 7 meters per second times 200 seconds. Put the units here, and I want to show you how units kind of work. Notice my seconds will cancel. I'm left with unit of meters only. 200 times 7 is 1,400 meters. So he travels 1,400 meters in that time. Now, I kind of cheated a little bit. If the displacement is equal to the distance, okay, so maybe I should have used d, because they were saying distance, right? If my distance and displacement are equal, what does that tell me? It tells me we went in a straight line. Okay? If my displacement had been less than my distance, it means I would have wandered a little bit and not gone in a straight line. So how long does it take a sprinter traveling at 9.5 meters per second to travel 400 meters? So again, we start with velocity equals delta x over delta t. Okay. And again, I'm looking for how long it takes, so I'm going to solve for delta t. Hopefully, with your practice on illicit equations, you should be able to do this with relative ease. Dividing by that, and delta x is 400 divided by 9.5. I don't feel like doing the calculation, but it should come out to be some form of, around 40 seconds, a little bit more than that, and it'll be in seconds. So you figure that out. You should have a calculator, hopefully, and do it on your own. All right, PowerPoint here, and move forward. So what about graphing? So when I graph, okay, is a great way of representing any types of velocity. Lots of graphs in this class. This will be our first opportunity to do it. So how do I make the graph meaningful? Well, if I want to graph velocity via distance and time graph, I want to make it mean something. And what I want to make it mean is the slope. I want the slope of my distance to time graph to be my velocity. If you notice, that means if I want delta x over delta t, that means my y has to be x and my t has to be, my y has to be displacement and my t has to be x. That makes sense. Hopefully time is generally the independent variable. That's almost always common. Time almost always goes on the x-axis. Okay? So take a moment, try this 2 questions real quick, and I'll get back to you. This one's not quite as hard. It should be pretty straightforward. All right. So, is this an example of constant velocity? And hopefully the answer is yes. Okay? The slope is constant. It's not changing. It's ever the same. How do you find this average velocity? Well, average velocity is delta x over delta t. Oops, that should be delta t. And x minus x naught over t minus t naught. or specifically the final point minus the initial point, which is 50 minus 0 over 5 minus 0, which is 50 over 5, which is 10 meters per second. So hopefully that one wasn't too difficult. Now, this one on the other hand can take you a little bit more time. So give this one a shot. I'll give you a minute or two. Pause this thing, give it a time, see what happens. When you're done, come on back. All right, so hopefully you've tried this question. Let's see how you get it. Which one of these three line segments, because there's three different slopes, so there's three different velocities. I hope you recognize that this slope right here is a flat line. That slope is 0. So if the slope is 0, that means my velocity is 0. In this segment, the velocity is down to the right, which means the velocity is going to be negative. I don't know what it is. I'm going to have to do a little bit of math to figure it out. And then, of course, this way, the slope is up and to the right, which tells me my velocity will be positive. What that number is, I'm not sure yet. So let's see how we go into calculate this question. So during what time interval, range, give me a range of values where my velocity is equal to 0? Well, I can do that a couple ways. I can say, well, I think it's 20 seconds to 30 seconds. You could write interval notation if you want. You could say t is less than or equal to 20, less than or equal to 30. Or you can even go into set notation and say bracket 20, comma 30 bracket, right? You can do it a lot of different ways. Hopefully you have those skills from Algebra 1 and Algebra 2. So during what time period is it negative? Well, it's 30 to 40 in terms of time. And when is that velocity, or what is that velocity during that interval? What you need to realize then is this 30 seconds would be your initial time, and this 40 seconds is your current time. And then you have a current and initial displacement, x, with it. So again, velocity equals delta x over delta t, which is x minus x naught over t minus t naught, which in this case, let's do our current position is 40 seconds is the time at it, and the current position is 0. Okay? My initial positions are at 30 seconds, and at 30 seconds, I have 100 meters. So I'm going to get a negative velocity. Now, what does negative mean? So 100 divided by 10 is negative 10 meters per second. Well, if this is x direction, we can take some implications from that. Positive would mean right, so negative would mean left. So if I were to say this verbally, I might say 10 meters per second to the left, because it shows as x. Okay. During what time interval is this positive? Well, it looks like it's positive from what, 0 to 20? Okay. 0 to 20 seconds. And hopefully you can do this same calculation. I want to leave some of this to you so that when I check it for your summer assignment, I can see that you have actually tried a few on your own. So 0 to 20, follow your procedure exactly in number 2 and do it again. Your answer is pretty straightforward. I think it's 50 divided by 20. Let's see, I think it's like 2.5 is about your answer. So it's 2.5 meters per second, positive, so or to the right. So hopefully you feel a little bit better about this, having tried a couple of them. But let's talk about one of our first difficult concepts. Okay? And this is where being in calculus or having had analysis already can help you a lot. Okay? And that's because we're going to use a little thing called a limit. Okay? Now, if you're scared of it, if you've never seen it before, it's actually not that big of a deal. All a limit says is when something gets really small or really close together, what's happening? Okay? Now, lots of things can happen with limits, so this is what we're talking about. So what is instantaneous velocity? What is my velocity at any given moment? Well, there's a problem with that. Velocity is a change in something. I can't do it at one moment. It has to have two moments. I've got to have my initial moment and my current moment. Well, the question of instantaneous velocity then says, what happens as I bring those two moments closer and closer together? And that's the definition of a limit, bringing those two guys closer and closer. So, in the case of velocity, I'm going to say, what happens to my velocity as I make my change in t little? Now, what's the best way to see this? I mean, obviously, I think this really does require a graph. Okay? We really need to talk about this in terms of a graph. So, let's take a look at a graph now. So, I've got 4 here. You should have some graph paper out. So let's take an example. We need to make some axes. Okay, so let's make an axis here. Remember, time is independent. Position is dependent, so we'll call that x. Okay. So, if I wanted to give an example of something that's more realistic, like say you're in a car, you start at position 0, you start at your house, okay? You speed up speed up, then you get on the interstate, drive at constant speed, you hit an accident, you slow down, and then you're chilling for a while, can't go anywhere, you're stuck there, okay? Finally, you're like, I'm fed up with this, and you just turn around and go back home as quickly as you can. Okay? And you make it back home. Okay? Now, what do I mean by instantaneous velocity? Now, first of all, I hope you recognize that if I asked for the overall velocity for this picture, my initial position, my final position are the same. And so my overall velocity is 0. So that's kind of a boring thing to talk about because lots of things happened in this example. So to only say, well, what's your average velocity really doesn't say the picture, doesn't sell the picture, doesn't really tell me what's happening. So although average velocity can be useful, it also can be misleading. Okay? That, right, I run a lap, you stop. And like, what's your velocity? And you're 0. I didn't do anything. My displacement's nothing. But that's not telling you the picture. You've got to be able to talk a little bit more carefully. So instead of taking the whole time period, we're going to bring the time period down to little teeny tiny pieces. Now what happens when you do that? Well, you create what's known as a tangent. Okay? If you say, what is the velocity right here? Let's do an easy example. When you're stopped. Okay? Hopefully everyone knows right here that my velocity equals 0, because you're not moving. Okay? But how would you find it if you didn't know? You draw yourself a tangent line from that point, and you look at the slope. And I hope you recognize that the slope right there is 0. And so my velocity at that point is 0. Now if I come over here and ask about your velocity, now your tangent line is going to be entirely different. I've got a positive velocity at that moment in time. Over here, I hope you recognize that we have a negative velocity. You can do a lot of things here, but the biggest thing is you got to talk about, can you look at overall shape? Okay? For instance, what's happening in cases like these? Okay? Now, don't get mixed up, because some people make a mistake. Okay? This is not an object moving in 2 dimensions. Okay? This is an object moving in 1 dimension. Okay? The dimension it's moving in is an x. The other dimension is time. Okay? Do not think that this is not projectile motion. Okay? This is one object. It starts real high, comes down close to wherever your original point is, and then it takes back off again and moves away from you. Okay? So in the case of if I was 0, maybe it's the ball flying in at me, stopping, and then flying back away from me. Okay? Only 1 dimension though. Okay? Only 1 dimension. Well, I hope you recognize over here we have a negative velocity, and over here we have a positive velocity. And we have a continuous graph. We're going to go slope. This is called concave up, right? If you've done an algebra 2 or analysis, it's a concave up graph. It curves over, and you have every slope in between from here to here. Okay? And I hope you remember you've also learned that at that vertex point, at that critical point, you have a slope of 0. So right here, I have a velocity of 0. So I have every value of velocity from here to here, including 0, and it ranges. Concave down. Instead of going from negative velocity to positive velocity, it's going to start at positive velocity, slow down, slow down, slow down, slow down, stop, and then it turns around, comes back towards you, and coming back towards you at a ever-increasing speed. It's getting faster and faster, okay? Negatively. Okay? We'll talk more about these graph matching exercises. We're going to spend an entire lab on this the first day of school. So if you're struggling with this a little bit, I understand that, but hopefully you got the idea, at least to start with. So let's go back to looking at your PowerPoint for a moment. All right, so now that we've done a couple graph matches, let's see if you can do one on your own. I've got 3 real quick pictures. I would like you to describe the motion in terms of velocity for each of these. I'll give you a moment. Pause it if you need to. All right, so the first one's kind of boring. Part A, what's going on? Well, nothing's going on in part A. My velocity is 0. My displacement is constant. Time's going by, but I'm just chilling right there the whole time. My movement on the y-axis is not going anywhere. That's me just, right? Okay. Part B. Well, my slope is constant. It's positive. So my velocity is constant and positive. Okay. Now that may mean to the right, it may mean up, it may mean a couple different things. Right now we're not too worried about where it's going, but it's a positive constant velocity. Let's take a look at our parabola one more time. So only half of my parabola, concave up. But again, if you look at your slope at first, it's slow, 0. The velocity is increasing over time. It's getting faster and faster. Okay? So here's what I'd like you to do. Number 2, graph me an example where my speed slows down. Didn't say velocity, said my speed slows down. There's lots of correct answers, but I'll give you a moment. Try that on your graph paper this time, and I'll show you on Promethean in a moment. All right, so hopefully you've got a couple ideas. So let's do a couple real quick. There's really 2 examples. There's a positive example and a negative example. And I'm going to draw both on the same graph, although you really should have only drawn one because they're independent events. To slow down, it must mean you started fast, which means you have to have a steep slope at first. So maybe something like, real steep slope. And then I need to slow down. So my slope needs to slow down. Now I want you to be very, very careful. I said speed. I don't care whether I was going positive or negative. I was just caring about the number. If you go a little bit farther and start doing that, you're speeding back up. But you're speeding up in the negative direction. The other example you could have done for slowing down was in the opposite direction. You go fast negatively at first, and then you slow down. What's an example of this, by the way? Square root function's pretty good for this, right? Well, our independent variable's t, right? So, square root function is an example. This is a few ones. It's half your parabola, right? The first half of concave down, the second half of a, first half for the concave down, second half for the concave up. But either way, hopefully you were able to come up with an example of that. So let's go back to our PowerPoint. Let's do a couple more things. We're almost done. This is the last new thing for today, and that's acceleration. And we got one more question after that, so that's not so bad. So now that you've seen that velocity isn't always constant, just like distance can vary and displacement can vary, which gives me velocity, velocity can vary over time, which gives me acceleration. Now, I'll tell you this, acceleration has no crazy scalar equivalent. Acceleration is always about direction. Direction is a very important piece to acceleration. Okay? So, acceleration, simply the rate of change of velocity. So again, second equation, maybe third equation possibly. We've got a velocity equation, we've got a displacement equation, now we've got an acceleration equation. Notice the symbology that's coming back. A equals, for acceleration, delta v over delta t. Now, just like anything, average of acceleration, we also have instantaneous acceleration. Okay? The limit again as t gets really, really small. Now, you're actually going to be in luck here. Okay? We don't deal with varying acceleration in an algebraic-based physics course. It's too hard. Okay? So this equation, though, you need to understand what it means, just like you understand looking at the slope. We're not going to be dealing with it too often. Okay? Now, really quickly, if I wanted to make a graph that made acceleration its slope, what would you want to graph? What 2 variables would you graph? Well, if you think back to the one we just did, it should make sense that t, again, is my independent variable. That's going to go on my x-axis. And then my y-axis isn't going to be displacement anymore. It's going to be velocity. And so now we have another graph that we'll spend much more time when we get into class with it than we will in here today. Right now, I just want you to be able to do this real baby version of acceleration at this time. Now, what's the units for acceleration? Velocity is meters per second. So you say it one of 2 ways. I like meter per second, or you can say meter per second squared. They're the same idea. Either way, it's all right. So last question, a little bit of mix, big question. This is kind of an example that I could give you for a quiz when you walked into class. This really does tell you a little bit about everything. Maybe if it was a quiz in class, I might have also asked about displacement and distance overall. So I'll give you a minute. This question may actually take you about 5 minutes. So take a moment, pause this. When you're done, when you think you have it right, press play and see how well you did. All right, so hopefully you're done now. Hopefully you've got it correct. Let's go to my Promethean board so that I can actually fill in the work myself. So a swimmer goes down a pool 20 meters long. So let's kind of do a little bit of vector here. So we start here, we go down 20 meters, and it took us 10 seconds to do that. Okay. And then he turns around, goes back 20 meters again, but this time it takes him 20 seconds. Well, what's his speed for the first half of the trip? Well, we know speed is simply distance over time. And well, that's 20 meters over 10 seconds, which is 2 meters per second. Notice it's a speed. I don't care about where I'm going. I don't care if I'm going away from the pool, towards, nothing. Direction doesn't matter here. Okay. What is the speed for the second half? Well, same equation. Speed is distance over time. The distance is the same, but this time he took twice as long, so his average velocity for the second half, or his average speed for the second half, is 1 meter per second. Well, what is the average speed? Now, here's a mistake you're going to make, and that's why I did this question, because it's a common mistake. Well, he went 2 for half, he went 1 for half, so it's 1.5 meters per second, right? But you've got to remember what the independent variable is. The independent variable is time. He did not swim 2 meters per second for half of it. He only swam for a third of it. So it's important that whenever you're looking at distance over time, that you actually think about it overall. What is the average speed? Speed of the whole trip, distance total, 20 down, 20 back, 40, over total time, 20 plus 10 is 30 seconds. And my speed is only 1.33 meters per second. Significantly slower than 1.5. Be very, very careful. You can never just average speeds or average velocities and expect that to be your actual average speed and velocity. You've always got to look at the whole picture. Okay? You've got to take it piece by piece. Well, what is his average velocity? Well, hopefully you know. That was a fun one. Boom. Now, let's talk about what's bad about this. If I'm giving credit for this, there's not much justification there. What I might want to see is something, say velocity equals delta x over delta t, and tell me, either 20 minus 20 or 0 over. Give me some indication that you understand displacement is 0. Because if I'm ever not sure about what you're doing, I look at the physics, I look at the work, I don't look at the answer. I'm looking for good physics, I'm not necessarily looking for good calculations. So whenever you just write an answer, if you ever do something like this, ever in my class, where you just put an answer down, and there's nothing on the paper that tells me why, it is your job to either tell me with an equation or with a sentence why that statement is true. You need to justify a statement like that. Okay? And that's going to be important for the AP too. If you ever just write the answer down, you do not get credit if you don't have some form of justification, whether it's algebraic or verbal. Okay, or written. All right, so E, let's throw in an acceleration question, and let's end our class with this. So if it takes him 6 seconds to slow down, turn around, and then get back up to full speed on the way back, what was his average acceleration in that time frame? Okay. Well, we know acceleration is change in velocity over change in time. Now, we need to make a choice. These velocities are different. One of these velocities is positive, and one of these velocities is negative. So I'm going to make the decision that his initial, this guy right here, was positive, and that this guy here is negative, because he's going the opposite way. Okay? So what you need to know is that when I changed my final position, the second half, negative 1 meter per second, okay? Minus, because it's change in is always minus, a positive 2 meters per second over 6 seconds, because that's how long it took to do it. Notice, it's not 2 minus 1, it's not 1. It's negative 3 meters per second over 6 seconds, which is 1/2 meters per second squared. Now, negative. Now, what's that negative mean? All that means is I slowed down at first. Depending on your frame of reference, which you'll read in the NIMSY notes, you could have gotten your answer positive here, but it wouldn't have hurt you either way. But the biggest thing is you needed to make sure you got a 3 here. If you got a 1 here, you weren't paying attention to direction when you did velocity. Okay. So, we're done with the lesson, but And you should basically be done with your summer assignment except for one thing. So the one thing I want you to remember is there's a 4-page document on NIMSY notes. It's very similar to this, explains everything thoroughly. There's about 5 examples in it. That's your last assignment. Get that done, put it in your notebook, and be out of here and be ready to go. You might want to memorize those cards you made for our 4 or 5 equations, though, so you're prepared the first day of school. But just as a reminder, let's talk about what we need. The first thing is, you should have the notes from this PowerPoint in your binder somewhere, okay, from this video. Okay. The second thing you should have is those yellow boxed-in equations. Should be on one of those index cards, okay, or more than one of them, and should be memorized by day 1. The third one is those NIMSY notes need to be done and completed on day 1. The last thing is make sure you put them in the homework section. It's not all that big. That math page section needs to be in there as well. I think that's page 5 and 6 or so in your summer assignment. And lastly, if you haven't had a chance to do it yet, get your parents to sign those administrative documents. If you need my calculator, get it. But anyway, no matter how you do it, we're done. We're out of here. See you on the first day. Hopefully it goes pretty well. Hopefully you have your calculator. Hopefully you're ready to do 2 labs. We're doing 2 labs on the first day. You're going to walk in and we're going to go outside in like 10 minutes. We're going to do a constant velocity lab. Then we're going to come in and we're going to play with this graph matching to hopefully improve your ability with that. So, but, you guys don't do this. Maybe I'm stuck doing a lecture in class. That's not fun. We want to play in class. I like to do the boring stuff at home. So let's hope you guys come prepared.